Dear students, welcome back to the lecture series on solid state. In this session, we will continue our discussion on crystalline solids. We will have a detailed explanation on different types of crystalline solids. We will also be discussing various intermolecular forces operating in solids, followed by the classification of crystalline solids and the properties of various solids. In the previous class, we have seen the differences between crystalline and amorphous solids. We saw that crystalline solids are characterized by a well-ordered, regular, repeating geometrical pattern throughout the entire three-dimensional structure. The constituent particles are well-ordered. On the other hand, amorphous solids have no particular order. The study of solid state is essentially a study of crystalline solid. Crystalline solids differ in the type of constituent particles. Also, there will be different kinds of intermolecular forces operating between the constituent particles. So, crystalline solids can be classified based on the type of constituent particles, that is, whether the constituent particles are atoms, whether they are ions or they are molecules. So, depending on whether the constituent particles are atoms, ions or molecules, and depending on the nature of intermolecular forces. Intermolecular forces are the forces that holds the particles together. So, depending upon these two, crystalline solids can be of different types. So, before moving on to the classification of crystalline solids, let us see what are intermolecular forces. Intermolecular forces are the forces of attraction or repulsion between molecules in a solid. It is the force that holds the constituent particles together. And these intermolecular forces determine the different properties of solids such as the melting point, hardness and solubility. Not only these properties but also several other properties like conductivity, etc. So, intermolecular forces are the forces of attraction or repulsion between molecules in a solid, and these forces are responsible for many interesting properties shown by solids. Now, let us see what are the different kinds of intermolecular forces seen in solids. We have the ionic forces or electrostatic forces, covalent forces, dispersion forces or London forces. We have dipole-dipole interactions. Hydrogen bonding is another intermolecular force. Also, metallic bonding is another intermolecular force seen in solids. Now, let us discuss about these intermolecular forces one by one. First is ionic forces, which is also known as electrostatic forces. Now, these are strong electrostatic attractive force between positively and negatively charged ions. Positively charged ion means a cation and negatively charged ion means an anion. So, between these two oppositely charged ions, there will be strong attractive force or electrostatic force of attraction, and such forces are called ionic forces or electrostatic forces. For example, NaCl the sodium ion Na plus and the chloride ion Cl minus. These two are oppositely charged ions and these are held together by strong electrostatic force of attraction to form the sodium chloride, which is an ionic solid. We will be discussing about ionic solids in the later sessions. Okay. So, ionic force or electrostatic force is a strong electrostatic force of attraction between a cation and anion. Now, this ionic force, which is a very strong force, contributes to high melting and boiling points, hardness, brittleness, etc. So, next is the covalent forces or covalent network forces. In such a force, the atoms are held together by strong covalent bonds in a continuous network. Now, how a covalent bond is formed? By mutual sharing of electron pairs. Now, such a bond is sufficiently strong bond, so that allows the atoms to order together, resulting in a huge continuous network. So, these are called covalent forces or network forces formed by strong covalent bonds. Covalent forces results in again very high melting points. They contribute to extreme hardness and electrical insulation. Except graphite, which conducts electricity. Again, we will be dealing with these properties in the later sessions. So, covalent forces or covalent network forces formed via strong covalent bonds results in a continuous network, and this is one of the forces generally seen in solids. So, next is about a very weak force or a non-covalent force called van der Waals forces or dispersion forces. It is more commonly known as London forces, named after the scientist London. Okay. So, we have van der Waals forces or dispersion forces. Now, what are these van der Waals forces? They are very weak, temporary, induced dipole interactions, or we may say a temporary dipole induced dipole interactions. Now, van der Waals forces results in low melting and boiling points since the force is very weak. The solids will have a soft texture and poor conductors of electricity. Now, let us see how this force operates. This is a very weak dispersion force. It is a dipole induced dipole interaction. So, on the screen you can see on the left side the formation of an instantaneous dipole moment on a helium atom. Now, there will be temporary variations in the electron density even in a nonpolar molecule. So, this temporary variations in electron density may create a temporary dipole or an instantaneous dipole. Now, this dipole may induce a dipole moment to the neighboring atoms or molecules, and that is why it is called a dipole induced dipole interactions. So, these temporary attractions between an instantaneously formed dipole and the neighboring dipoles are called dispersion forces. And since these are very temporary attractions, dispersion forces are generally very weak. So, next intermolecular force that is commonly seen in solids is the dipole-dipole interactions. Now, what are dipole-dipole interactions? It is the attraction between a partially positive and partially negative ends of polar molecules. For example, consider the case of HCl. Hydrogen is electropositive and chlorine is electronegative. So, hydrogen may attain a partial positive charge, whereas chlorine may attain a partial negative charge. So, in result, there will be a slight charge separation or partial charge separation in this molecule, resulting in a dipole moment. The partial charge separation between the two atoms results in a permanent dipole moment, and this dipole moment contributes to dipole-dipole interactions. For example, consider HCl, hydrogen with a partial positive charge and chlorine with a partial negative charge. Now, if we have another molecule of HCl, that is again another dipole with a partial positive charge on the hydrogen and a partial negative charge on the chlorine. So, this is one dipole, this is another dipole. Now, what are dipole-dipole interactions? The attraction between partially positive and partially negative ends of polar molecules. So, here the negative end of one chlorine atom will get attracted to the partially positive end of hydrogen atom of another HCl. So, there will be a dipole-dipole interaction. Okay. So, dipole-dipole interaction, it is a relatively strong, okay, not much strong as a covalent bond or covalent interaction, but relatively strong dipole-dipole interaction. It is an attraction between partially positive and partially negative ends of polar molecules. On the screen, you can see an animated picture of the interaction of dipoles. So, here you can see that the positive end of one dipole getting attracted to the negative end of another dipole. Okay. The molecules will have a permanent dipole moment. So, this dipole-dipole interaction between the two molecules. Another intermolecular force that can be seen in solids is hydrogen bonding. Hydrogen bonding is a special case of dipole-dipole interactions. We have seen earlier that dipole-dipole interactions normally occur in polar molecules. So, hydrogen bonding is a special case of dipole-dipole interactions where the interactions are much stronger than normal dipole-dipole interactions. And here the hydrogen is bonded to highly electronegative atoms such as nitrogen, oxygen or fluorine. So, when the hydrogen atom is attached to electronegative atoms such as nitrogen or such as an oxygen or fluorine. So, this results in hydrogen bonding. And hydrogen bonding can result in higher melting and boiling points than we normally expect, and they also results in crystalline structure with open spaces. Another intermolecular force that can be seen in solids is metallic bonding. In metallic bonding, the positive metal ions are surrounded by a sea of delocalized electrons that move freely. Okay. In ionic forces or electrostatic force of attraction, it is an attractive force between a positively charged cation and a negatively charged anion. But here we have a positively charged metal ions. This is also a kind of electrostatic attraction, but instead of attraction between a cation and an anion, we have positively charged metal ions surrounded by a sea of electrons, surrounded by a pool of electrons. And there will be attraction between these positively charged metal ions and the surrounding free electrons. And metallic bonding is responsible for high electrical and thermal conductivity, malleability, ductility, metallic cluster, etc. So, these are the different kinds of intermolecular forces in solids. We had ionic force or electrostatic force, which are very strong. We had dipole-dipole interactions, dispersion forces or London forces. We have covalent forces, hydrogen bonding, metallic bonding, etc. Now, depending upon which kind of intermolecular force is present in a solid or which kind of constituent particles, that is atoms, ions or molecules are present, crystalline solids can be classified into molecular solids, covalent or network solids, ionic solids and metallic solids. First, let us see about molecular solids. Molecular solids are those in which the constituent particles are molecules. For example, carbon dioxide. Solid carbon dioxide is an example for a molecular solid. Iodine is an example for a molecular solid. Molecular solids can be further classified depending upon the nature of intermolecular forces present in it. They can be non-polar molecular solids, polar molecular solids or hydrogen bonded molecular solids. Now, let us see them one by one. What are non-polar molecular solids? As the name suggests, in non-polar molecular solids, the constituent particles are either atoms or non-polar molecules. The constituent particles which have atoms or non-polar molecules are called non-polar molecular solids. Now, what is the type of intermolecular force present in it? Non-polar molecular solids are held by weak dispersion forces or London forces. We have already discussed about weak dispersion forces. It is a kind of dipole-induced dipole interaction. It is normally very weak. So, in non-polar molecular solids, these atoms or non-polar molecules are held together by very weak dispersion forces or London forces. They are very soft solids with low melting points, and they are also very poor conductors of electricity or non-conductors of electricity. Small symmetrical molecules such as hydrogen, nitrogen, oxygen, fluorine, etc. They have very weak attractive forces and they form molecular solids with very low melting points. For example, carbon dioxide, solid carbon dioxide, which is also known as dry ice, consists of small non-polar molecules and they form a molecular solid with a melting point of -78°C. On the other hand, substances consisting of larger non-polar molecules have larger attractive force and they melt at higher temperatures. For example, iodine. Iodine is a non-polar molecular solid. This is a large molecule and it melts at 114°C. So, next is about polar molecular solids. And again, as the name suggests, these are solids in which the constituent particles are polar molecules. And what will be the intermolecular force in such solids? Polar molecules are held together by strong dipole-dipole interactions. We have already discussed about dipole-dipole interactions. So, dipole means it will have a slight charge separation having two ends, that is a slightly positively charged end and a partially negatively charged end. So, such dipole-dipole interactions will exist in polar molecules or polar solids. And these solids will be made up of molecules that have a permanent dipole moment. These are generally soft solids with higher melting points than non-polar solids. They will also be non-conductors of electricity, and they generally will be in the liquid or gaseous state at room temperature and pressure. Given here are two examples of polar solids. We have HCl and sulfur dioxide SO2 both in the solid state. So, in hydrogen chloride, as we discussed earlier, it is a molecule with a permanent dipole moment. It is a polar molecule with hydrogen attaining a partial positive charge and chlorine attaining a partial negative charge, forming a dipole. Now, this will get attracted to another molecule of hydrogen chloride, creating dipole-dipole interactions. Having a dipole-dipole interaction. So, next is hydrogen bonded molecular solids. We have seen that hydrogen bonding is a special case of dipole-dipole interaction. So, in this, the constituent particles are polar molecules and they are held together by hydrogen bonding, and they are generally non-conductors of electricity, and they are volatile liquids or very soft solids under room temperature and pressure. These are some examples of hydrogen bonded solids. We have hydrogen fluoride, ammonia. Another example is ice, that is solid water. So, in ice, in order to maximize the hydrogen bonding, when fixed in position as a solid, the molecules can adopt a tetrahedral arrangement, as you can see in this figure. So, this tetrahedral arrangement of ice results in an open cage-like structure of ice. So, this open cage-like structure results in the properties different from that of liquid water. So, next category of crystalline solids are the covalent or network solids. In covalent or network solids, the constituent particles are non-metallic atoms, and these non-metallic atoms can be same or different. And as the name suggests, in covalent or network solids, the particles are held together by strong and directional covalent bonds in a continuous network, resulting in huge crystals. The covalent bond is sufficiently strong. The non-metallic atoms can be attracted to each other via covalent bonds, resulting in a continuous network and forming giant crystals. And as a result, covalent solids or network solids are also called giant molecules. They are generally very hard with extremely high melting points, and they are also poor conductors of electricity. Let us see some examples for covalent solids. Diamond is a three-dimensional crystal and it is a covalent network solid, and in this each carbon atom from its structure makes 4 covalent bonds to 4 other carbon atoms, forming a network. Another example is graphite. Graphite is again consisting of carbon atoms, but it is a 2D network solid composed of planar sheets of covalent crystals that are held together in layers by non-covalent forces. Now, what are these non-covalent forces? It's nothing but these van der Waals interactions or weak dispersion forces. So, in graphite, there is covalent bonding between the carbon atoms, but these carbon atoms, each of these have a planar structure which are arranged in layers one over the other, and these layers are attracted via dispersion forces or non-covalent forces. And since the force between these layers are very weak, the layers are relatively slippery and they can slide past each other. Also, because of this, graphite is very soft and electrically conductive, unlike other covalent solids. So, next example is fullerenes or Buckminster fullerene, which is a carbon 60 molecule, C60 molecule. It is a sphere composed of 6-membered and 5-membered carbon rings. As you can see here, has alternating 5-membered as well as 6-membered carbon rings, again consisting of carbon atoms only connected via covalent bonds, and these are more generally known as buckyballs. This buckyball exhibit unique structural, chemical, electronic and thermal properties, and these properties are due to its highly symmetrical icosahedral structure, as you can see in this figure, that contains a mixture of single and double bonds. So, we have seen 3 examples for a covalent network solid. We have diamond, graphite and fullerene, all consisting of simple carbon atoms, but their properties are different, and that is why these are called the allotropes of carbon. Covalent network solids also include crystals of some other nonmetals or some covalent compounds such as silicon carbide, also known as carborundum, which is used as an abrasive on sandpaper. Many other minerals like amethyst, rubies, sapphire all have networks of covalent bonds. Now, next category of crystalline solids is ionic solids. As the name suggests, the constituent particles are ions. Now, what will be the intermolecular force present in it? The cations and anions will be held together by strong electrostatic force of attraction or strong Coulombic force of attraction. Ionic bonds occur between a metal, usually as a cation which is smaller in size, and a non-metal, usually as anion which is bigger in size. A typical example for an ionic solid is given here, sodium chloride, NaCl. So, there will be attraction between sodium, which is a cation, Na plus, and chlorine, which is an anion, Cl minus. So, strong Coulombic force of attraction between this will result in a strong ionic solid. Ionic solids are very hard, brittle, they have high melting point, they are also electrical insulators or poor conductors of electricity. However, they can conduct electricity in the molten state or when dissolved in water. In the molten state or when dissolved in water, ions will be more free to move and hence they can conduct electricity. However, they remain poor conductors of electricity in the solid state. We have seen NaCl as an example for the ionic solid. Similarly, calcium fluoride is another example for ionic solid. So, next is metallic solids. We discussed about metallic bonding, in which the metal ions are attracted to a sea of delocalized electrons. So, in metallic solids, as you can see in this figure, there will be positively charged metal ions or cations, and they are attracted to each other in a cloud of electrons or a sea of electrons, and these electrons are mobile or they are very free to move, and that's why it's called a sea of electrons. The binding force here is electrostatic force of attraction. Metallic bonding is seen in all metals including gold, silver, platinum, iron, etc. So here you can see silver as an example. We have Ag plus cations surrounded by many free electrons. Metallic bonding is responsible for many interesting properties of metallic solids. Unlike other solids, metallic solids have high electrical and thermal conductivity due to the movement of free electrons. They are also characterized by high melting points like tungsten, which has a higher melting point of 3400 degrees Celsius. For aluminium, it is 660 degrees Celsius. Except for the alkali metals of group 1, they generally have low melting points. Potassium has 63.38 degrees Celsius. Metallic solids are characterized by their ductility and malleability, or metallic solids are considered malleable and ductile. They can be flattened into thin sheets or they can be drawn into long wires, and it is because that the bonds between the atoms allow them to slide over each other, and that give rise to the malleability and ductility in metallic solids. Another interesting property shown by metallic solids is their luster. Again, because of the delocalized electrons in their structure, they can reflect light, making metals to exhibit a shiny appearance or a lustrous appearance. So today, we had a detailed discussion on different types of crystalline solids. They can differ in the type of constituent particles and the nature of intermolecular forces present in it. We discussed about different types of intermolecular forces such as ionic forces, dipole-dipole, van der Waals, covalent forces, hydrogen bonding, metallic bonding, etc. The main types of crystalline solids: ionic solids, metallic solids, covalent network solids and molecular solids. And we have seen that the nature and strength of the intermolecular forces determine the properties exhibited by various solids. Now let's discuss some questions based on this session. These are some assignment questions. We will discuss the answers in the next class. So the first question is, the molecules in polar molecular solid are held together by dipole-dipole interaction, London forces, ionic bond and metallic bond. Question number 2, which type of solids are formed by three-dimensional arrangement of cations and anions bound by strong electrostatic force? You have 4 options: polar molecular solids, ionic solids, covalent solids and metallic solids. Which type of crystalline solid is also called as giant molecules? Ionic solids, covalent solids, polar molecular solids and metallic solids. Question number 4, which of the following are responsible for high electrical and thermal conductivity of a metal? Options given are ions, covalent bonds, free H plus ions, free and mobile electrons. And the last question, which of the following is non-conductor of electricity at solid state but can conduct electricity in the molten state or when dissolved in water? Options are non-polar molecular solids, metallic solids, ionic solids, hydrogen bonded molecular solids. Please try to find out the answers. We will discuss it in the next class. Also, we will see more interesting aspects of crystalline solids in the next class. Thank you.